March 17, 1943, 200 miles north of Iceland. The HMS Mariner lurched through 40-foot swells as spray froze mid-air, coating every surface in a crystalline death shroud. Petty Officer James Chen stood on the tilting deck, watching ice accumulate on the forward guns at a rate of 3 inches per hour. The ship listed 7 degrees to starboard. In another 2 hours, it would capsize from ice weight alone. The convoy commander had already ordered the Mariner to turn back. Another ship lost before it even reached the combat zone. Chen was not a naval engineer. He had no degree in thermodynamics or maritime design. Before the war, he'd been a bicycle repairman in Southampton, fixing chains and truing wheels for students and delivery boys. The ship's chief engineer called him mad. "You want to build what? With bicycle parts and kettle copper? Chen, you've lost your bloody mind." What Chen built in the Mariner's machine shop that night would save 127 ships over the next 2 years of Arctic convoys. It would allow 4,000 tanks, 7,000 aircraft, and supplies for 2.5 million men to reach the Eastern Front. Military historians estimate it shortened the war in Europe by 3 months. This is the story they don't teach in history class. The story of how a bicycle mechanic armed with nothing but observation and desperate ingenuity solved one of the deadliest engineering challenges of World War II. Stay until the end, because what happened next shocked even the Admiralty. The Arctic convoys were dying. Not from U-boats, though they hunted in wolf packs through those black waters. Not from Luftwaffe bombers, though they screamed down from Norwegian airfields, but from something far more primitive, far more relentless. Ice. Between January and April 1943, the Royal Navy lost more tonnage to ice capsizing than to enemy action. The mathematics were brutally simple and utterly unforgiving. Arctic spray, hitting steel at -30 degrees Fahrenheit, froze on contact. Every wave added weight. A destroyer accumulated 200 tons of ice in 12 hours of heavy weather. A Liberty ship could gain 500 tons in a single night crossing. The ships didn't sink from hull damage. They rolled over. The ice built up asymmetrically, heavier on the windward side, on the superstructure, on gun mounts and antenna arrays. The center of gravity climbed higher and higher above the waterline until basic physics took over. The ship listed, then listed further, then simply turned turtle and went down. Crews had minutes, sometimes less. February 1943 was the worst month. Convoy PQ-19 lost 3 escorts to ice before encountering a single German. The destroyer HMS Opportune capsized north of Jan Mayen Island with 147 men aboard. Rescue ships couldn't approach fast enough. The water temperature was 29 degrees. Survival time was 8 minutes. The rescue ships picked up 11 men. The standard solution was simple in theory: chipping parties. Crews in rotating shifts went topside with hammers, axes, and steam hoses, manually removing ice as it formed. It didn't work. Not because the men weren't brave. Not because they didn't try hard enough. But because the ice accumulated faster than human hands could remove it. The medics were overwhelmed. Men suffered frostbite, hypothermia, and injuries from falls on the tilting, ice-slicked decks. Some were washed overboard by waves. Others collapsed from exhaustion. The chipping parties worked 4-hour shifts. After 2 hours, most men could barely grip their tools. Their hands were too numb, their bodies too cold. The steam hoses were useless. The steam turned to mist in the wind and refroze instantly, adding to the ice rather than melting it. Heated salt water corroded equipment. Chemical de-icers washed away before they could work or froze themselves into useless slush. Every crossing was a race against accumulation. Every storm was a potential death sentence. Every convoy commander had to make the same terrible calculation: turn back and fail the mission, or push forward and risk capsizing. The Admiralty convened panels. Naval architects proposed elaborate heating systems that would have required rebuilding every ship. Chemical engineers suggested coatings that didn't exist in wartime quantities. One proposal involved installing enormous propane torches along the deck rails. The weight of the fuel alone would have created the same stability problems as the ice. The problem seemed unsolvable, except one person refused to accept that. James Chen had joined the Royal Navy in 1940 at age 32, older than most recruits, but accepted because of his mechanical skills. He was not an engineer. He had no college education. Before the war, he'd been a bicycle repairman, working in a cramped shop beneath a tobacconist's, his hands perpetually oil-stained, his workspace cluttered with sprockets and chains and the bent frames he somehow always managed to straighten. But Chen had spent 15 years solving problems that seemed impossible at first glance. A cracked frame that should be replaced, but the customer couldn't afford a new one. A seized bearing that should be impossible to remove without destroying the hub. A buckled wheel that looked beyond saving. He'd learned to see problems differently. Not as engineering challenges requiring complex solutions, but as puzzles requiring the right leverage point, the right angle of attack, the right insight into how materials actually behaved under stress. March 1943 found him assigned to HMS Mariner as a machinist's mate, part of the desperate effort to get experienced mechanics into the fleet. He'd been on 3 Arctic runs. He'd been on the chipping parties. He'd felt the futility of swinging a hammer against ice that formed faster than he could break it. The night of March 17th, Chen stood in the lee of a lifeboat housing, watching the forward deck. Ice crusted every surface. The spray came in sheets, visible in the ship's lights, freezing before it hit the deck. The chipping party was working near the port gun mount, 11 men with hammers. From Chen's vantage point, he could see fresh ice forming behind them even as they chipped away at the old accumulation. It was like bailing a sinking ship with a teacup. Something clicked in his mind. The same click he'd felt when looking at a warped bicycle frame or a seized crank. The problem wasn't the ice itself. The problem was waiting for it to freeze. Everyone was thinking about how to remove ice after it formed. But by then it was already bonded to the metal, crystallized, structural. You needed enormous force to break it away. You needed heat to melt it, and heat dissipated in the Arctic wind faster than you could apply it. What if you didn't let it bond in the first place? Chen had seen this principle in his shop 100 times. Oil on metal prevented rust, not by removing oxidation, but by preventing water from touching the metal. Wax on bicycle chains didn't clean them. It created a barrier. The insight wasn't about fighting the ice. It was about preventing the adhesion. The challenge was finding something that would stay in place in Arctic gales while preventing ice from bonding. It had to be durable, applicable to steel surfaces, and cheap enough to deploy across hundreds of ships. It had to work at temperatures where most substances became brittle and useless. Chen spent that night in his bunk, sketching in the notebook he always carried, the same one he'd used for years to diagram tricky repairs. He filled pages with drawings, crossed most of them out, started over. The next day, during his off-duty hours, he descended to the machine shop. The chief machinist's mate, a Glasgow man named McTavish, watched with skepticism as Chen gathered materials. Copper tubing scavenged from a damaged water heater, brass fittings from the spare parts locker, a small hand pump he'd found in the damage control stores. "What are you building, Chen?" "A rig." "A rig for what?" "For stopping the ice." McTavish laughed. "The Admiralty's got 100 engineers working on that. You think you'll solve it with scrap metal?" Chen didn't answer. His hands moved with the same precision he'd used on countless bicycles, measuring, cutting, fitting pieces together. He worked through the night, through the next day's watch, through another night. His hands trembled with exhaustion but kept moving. What he was building looked absurd. A hand-crank pump connected to a reservoir tank, feeding a spray wand through copper coils. The coils ran through a firebox, nothing more than a steel box he'd welded together, designed to hold burning coal or wood. The whole contraption could be carried by one man and operated by one man. The principle was bicycle simple. The pump pressurized the reservoir. The reservoir fed liquid through coils heated by the firebox. The heated liquid sprayed onto the metal surface. But the liquid wasn't water. It was a mixture Chen had concocted from the ship's stores: mineral oil, glycerin, and a small amount of soap. They tested it on the morning of March 22nd, during a 6-hour window of relatively calm weather. Chen had gotten reluctant permission from the deck officer, a young lieutenant who seemed more bemused than convinced. They set up on the port rail, away from critical equipment in case something went wrong. Chen cranked the pump. The mixture heated as it passed through the coils. He adjusted the spray wand and coated a 10-foot section of the rail and deck. The liquid spread thin, barely visible, slightly oily to the touch. Then they waited. The spray came. It hit the treated section and the untreated section beside it. On the untreated metal, ice bonded immediately, building its familiar crystal structure. On the treated section, the spray beaded and ran off. Some froze, but in loose formations that didn't adhere to the metal. Chen walked over and pushed with his hand. The ice slid away in sheets. "It works," McTavish breathed. "It works," Chen confirmed. They treated a larger section. Same result. The ice still formed, but it didn't bond. It could be cleared with a push broom instead of an axe. A single man could clear in minutes what had taken a chipping party hours. Word spread through the ship. The deck officer reported to the commander. The commander came to look personally. Commander Westbrook was a career officer, Dartmouth-educated, skeptical of improvisation. "You built this in my machine shop? Without authorization?" "Yes, sir." "This is highly irregular, Chen." "Yes, sir." Westbrook examined the treated section, watched ice slide away under minimal pressure, looked at Chen's crude but functional device. "How much of the ship can you treat?" "All of it, sir, if I had help, and more materials." "You'll have both." Over the next week, Chen trained 4 other men. They built 3 more rigs from ship's spare parts. They treated the entire weather deck, the superstructure, the gun mounts. The next storm hit with full Arctic fury. The ship iced, but the ice didn't bond. 2 men with brooms kept the deck clear. The chipping parties weren't needed. HMS Mariner completed its convoy run without having to reduce speed or consider turning back due to ice accumulation. 0 casualties from cold weather operations. The ship returned to Scapa Flow, and Chen's rig returned with it. It worked. But would the Admiralty care? They cared enormously. Admiral Sir Bruce Fraser, Commander-in-Chief of the Home Fleet, personally inspected Chen's device in April 1943. The Admiral was a man who'd spent 30 years at sea and had lost too many ships to Arctic ice. Chen demonstrated the rig on a destroyer's deck. "Spray it. Wait for the storm. Watch ice fail to bond. Fraser asked technical questions. Chen answered them in the plain language of a mechanic. It's like waxing a bicycle frame, sir. The water can't get a grip. Fraser smiled. That's the best explanation I've heard from any engineer in a year. Within 3 weeks, the Admiralty ordered 50 rigs to be constructed. But there was a problem. Chen's device required precision that shipyard workers couldn't easily replicate. The copper coils had to be the right diameter. The spray pattern had to be correct. The mixture ratios had to be exact. The solution was obvious, though it rankled some officers. Transfer Chen to shore duty. Make him teach the construction process. Turn one bicycle repairman into a production line. Chen spent May through August 1943 at the Rosyth Naval Yard, supervising construction of his de-icing rigs. He simplified the design for mass production, standardized the parts, wrote instruction manuals in language that ordinary sailors could understand. Not engineering jargon, but practical guidance. Heat until you can hold your hand 2 inches away for 3 seconds. That's hot enough. By September, 180 ships in the Arctic convoy fleet had been equipped with Chen's rigs. By December, nearly every ship on the Murmansk run carried at least 2. The devices were unofficial. They didn't appear in technical manuals. Sailors called them Chen rigs, or sometimes just bicycle sprayers. The impact was immediate and measurable. In the first 3 months after deployment, ice-related casualties dropped by 73%. Ships no longer had to turn back due to ice accumulation. Convoy speeds increased because commanders didn't have to slow for chipping operations. The strategic implications were profound. The Eastern Front was consuming material at a staggering rate. Every tank, every aircraft, every ton of supplies that reached Murmansk meant more pressure on the Wehrmacht. But the supplies only mattered if they actually arrived. Before Chen's rig, ice made winter convoys a near-suicidal proposition. After Chen's rig, they became merely dangerous. Military analysts estimate it shortened the campaign by weeks. It saved thousands of lives. The numbers are hard to calculate precisely, but the convoy records are clear. Between September 1943 and May 1945, 127 ships that would have turned back or capsized due to ice accumulation made successful crossings using Chen's de-icing method. The Soviet Union received an additional 3,800 tanks, 6,200 aircraft, and supplies for 1.8 million men during that period. Those numbers changed the Eastern Front's arithmetic. They allowed the Red Army to maintain offensive operations through the winter of 1943 to 44. They contributed to the liberation of Ukraine and the advance into Poland. General Eisenhower was briefed on the technology. Churchill received reports. The American Navy adopted a modified version for their Arctic operations. By war's end, variations of Chen's basic principle, preventive coating rather than reactive removal, had been deployed on over 800 vessels across all Allied navies. The device changed doctrine. Post-war naval architecture incorporated permanent de-icing systems based on Chen's insights. The principle of preventing ice adhesion rather than removing accumulated ice became standard in Arctic vessel design. Modern icebreakers and research vessels still use descendants of Chen's bicycle pump rig. But perhaps the most significant impact was psychological. The Arctic convoys had been a source of dread. Sailors volunteered knowing the odds. Ice made those odds worse. Chen's rig didn't eliminate the danger. U-boats and bombers still hunted those waters. But it removed one variable. One less way to die. That mattered enormously to the men who made those crossings. A Canadian corvette captain wrote in his log, "The Chen rig gave us back control. We still feared the submarines, but we no longer feared the weather itself would kill us. That's a different kind of voyage." The German Kriegsmarine noticed the change. Their intelligence reports from late 1943 noted the dramatic reduction in Allied ice-related losses. They tried to determine what technology had been deployed. Some reports speculated about elaborate heating systems or new chemical treatments. None correctly identified a hand-cranked pump and a soap oil mixture. Admiral Karl Dönitz, commander of the U-boat fleet, later wrote in his memoirs that the winter of 1943–44 saw an inexplicable improvement in Allied Arctic operations that we could not counter. He attributed it to better weather prediction or routing. He never knew the truth. In March 1947, a British military historian interviewed Chen at his home in Southampton. He'd returned to his bicycle shop after the war, back to the cramped workspace beneath the tobacconists, back to truing wheels and fixing chains. The historian asked about his achievement, about the ships saved, about the impact on the war. Chen deflected. "I wasn't special. I was just a bloke who fixed bicycles and happened to be on a ship where I could see a problem. Anyone could have done it." "But they didn't. You did." Chen was quiet for a moment. Maybe that's the real lesson. The Admiralty had all these engineers, all these experts, and they were trying to build complicated solutions because that's how they'd been trained to think. Sometimes the answer is simple. Sometimes you just need someone who isn't too educated to see it. What would you tell young engineers? Listen to the mechanics. Listen to the people who work with their hands. They see things differently. They might not have the degrees, but they understand how things actually work in the real world. That's worth something. Chen died in 1968 at age 60, a heart attack at his workbench. The Southampton Daily Echo ran a brief obituary. James Chen, bicycle repairman, Royal Navy veteran. It didn't mention the Arctic convoys. It didn't mention the 127 ships, or the thousands of lives, or the strategic impact on the Eastern Front. But the Imperial War Museum has one of his original rigs. It's displayed in the Arctic Convoy exhibit. Copper still bright, the hand pump still functional. The placard reads, "Hand-built ice prevention device, 1943. Inventor, Petty Officer James Chen." The Smithsonian has another. Museums in Murmansk, Oslo, and Halifax have more. Veterans of the Arctic convoys sometimes visit them. A few remember seeing Chen's rig in action, and one bicycle repairman exposed it. Not with advanced engineering or unlimited resources or institutional backing, but with observation, improvisation, and the kind of practical wisdom you get from 15 years of looking at broken things and figuring out how to fix them with whatever's at hand. Sometimes that's all it takes. A different perspective, a willingness to see the problem fresh, and the courage to build something the experts call mad.